Right, let's have a look at this then. So we have a roller coaster, which there's a motor. It says there is a motor. The motor takes it to the top. At the top, it has gravitational potential energy. It free falls down this drop, and as it does so, what happens to the gravitational potential energy? Well, it is converted to kinetic energy, right? What you've got to remember with all these questions is that it's work done and it's energy, but it's all about the principle of conservation of energy, okay? You can't create energy, you can't destroy energy. What happens with energy is that it turns from one type into another type, okay? So we can calculate GPE, we can calculate KE. Sometimes we can assume that it's 100% efficient. That means there's no energy lost. But be careful when you say energy is not lost. Energy at times is dissipated because of resistive forces like friction and air resistance. Okay, it's not lost. It's transferred to internal energy, to thermal energy of the air particles or whatever it is. So it's dissipated because there's some work done to overcome friction. So whatever that is up there might not all turn into kinetic energy because there's some work done against friction. All right, let's have a look in the data booklet at what we've got. These are all your formulas. So we've got this one here, W equals Fx cos theta. That W, that's your work done. So work done is force times distance. That's an energy with height in it, so that's your GPE. That's an energy with the spring constant in it, so that's that's elastic energy. And then this one here with velocity in it, that's your kinetic energy, okay? Then we have this one here, Fx. What's Fx? Right, that's your work done, isn't it? So any work done is equal to, and this is quite an interesting one because here is the difference between two kinetic energies. So could be kinetic energy has been lost due to work done overcoming friction, or it could be a GPE, take away a KE. You can make this equation up yourself, okay? But it's based on the principle of conservation of energy, right? That's one more that we might use. Power is work done over time. And remember, work done is equivalent to energy transferred. So work and energy both in joules. The last one then is the efficiency equation, which is useful over total times 100. So those are all your equations, right? And that is your question, okay? Let's have a little look then. What does it start with? It says the motor power output is 65 kilowatts. Let's write a little list of what we know. Power equals 65 kilowatts. We know the mass is 2,600 kilograms, and we've got a time to get to the top is 32 seconds. We've also got these heights, look. All right. Work done by the motor, show that the work done by the motor in 32 seconds is approximately 2 megajoules. So basically this means calculate work done and prove that that's the answer. All right, so we know power, we know time. This is the one we need. Power equals work done over time taken. Right, power equals work done over time taken. We can rearrange that to give us W equals P times T. And you'll see that that should give you an answer. I get 2.08 times 10 to the 6 joules, which is approximately 2 megajoules. Okay? Right, so that is the work done by the motor. Now it says calculate the efficiency of the mechanism, assuming the carriages are momentarily at rest. So what we're assuming now is that all that energy that the energy transferred by the motor, or the work done by the motor, is all going to be turned into, all those joules, those 2 megajoules, are all going to be turned into GPE. Well, let's see. If they are, it's 100% efficient. If there's some energy lost, well, we can calculate that efficiency. So 3 marks for this. There's a lot of work in this. Let's find the GPE at the top, right? Using that equation, delta E equals mg delta H. Okay, so the change in height is the 42 meters. So it's, what was our mass? 2,600 times 9.81 times 42 meters. And you will get something in the region of 1.07 times 10 to the 6 joules. Okay, so that's our GPE. All right. Does all that turn into GPE? No, it doesn't, does it? So how do we find the efficiency? Right, the efficiency is the useful divided by the total input times 100. So the useful bit, well, that's what we wanted, was the GPE. So the efficiency is the useful bit, which is the GPE, over the total. I'm going to use, rather than the rounded number, I'm going to use the 2.08, I think, times 100. And you'll get an efficiency of 51.5%. Okay, so remembering efficiency equals useful output over total input times 100%. All right, so that's the first bit. Okay, now second bit. Let me turn over because I've got this on the back. Now it says at B, the carriages become disconnected, right? So at B, the carriages become disconnected from the motor and they move under the influence of gravity for the rest of the ride. In moving from B to C, a distance along the track of 36 meters. So coming down that track, that distance is 36 meters. Okay. The carriages experience a mean resistive force. So that means all your friction, all your air resistance, the resistive force is 2.8 kilonewtons. And that's the distance. Okay. So we know a force and we know a distance. We could now work out the work done to overcome all those resistive forces. Okay. So work done against friction, against resistive forces, W equals F times X. The force, it tells me, is 2.8 kilonewtons. So I'm going to do 2.8 times 10 to the 3 multiplied by the distance of 36 meters. So W equals, put that in your calculator, 1.01 times 10 to the 5 joules. Okay, so we've got the work done against friction. Let's look at these energy changes again. All right, so we've got gravitational potential energy up here, some work done against friction being the difference, but the GPE is converted to KE. Okay, now we worked out the GPE up here, but we worked it out actually for coming up from A, that 42 metre distance. So actually, if you look, what we're interested in now is just that drop from B to C. So actually, in calculating this GPE, if I actually, because this is where we want to know this is the bit we're interested in at C, isn't it? We want to know the speed. We need to know the kinetic energy to find the speed at C. So let's work it out. We've got the GPE at C. Take away the work done against friction. That will tell us the kinetic energy. Oh, sorry, that's GPE at B. That will tell us the kinetic energy at C. All right, so the GPE at B is mgh, so that's 2,600 times 9.81 times our 30 metres, all right, and that, try that, pause and pop that in your calculator, but that is 7.65 times 10 to the 5. We know that. We can work out this, can't we? So the kinetic energy at C is this GPE. So that number for GPE. Take away the work done, which is this one, 1.01 times 10 to the 5. Okay. And that gives us 6.64 times 10 to the 5 joules. So we know the kinetic energy. We can now work out the speed, because remember, kinetic energy equals a half mv squared. All right, so v is the square root of 2 times ke over m. So that's the square root of 2 times 6.64 times 10 to the 5 over, what was it, 2,600. Okay, 22.6 metres per second.